Scientists have recently uncovered a surprising revelation with potentially profound implications for life on Earth. The moon is shrinking. This unexpected phenomenon, observed by researchers, entails a gradual reduction in the size of our nearest celestial companion. As a result, the moon is experiencing landslides and instability, particularly at its south pole. This discovery is both intriguing and significant, offering valuable insights into the moon's evolutionary processes and posing questions about the future of human exploration. But what exactly is causing the moon to shrink, and how does it affect us? Join us as we delve into the fascinating details of how scientists stumbled upon this phenomenon, the compelling evidence supporting it, and the array of challenges and opportunities it presents for forthcoming missions to the lunar South Pole. Don't forget to stay tuned till the end and show your support by liking and subscribing. The mystery behind the moon's shrinking can be attributed to two primary factors: the cooling of the moon's interior and the tidal forces exerted by Earth. Firstly, like any celestial body, the moon was incredibly hot during its formation around 4.5 billion years ago. However, as time progressed, it gradually cooled down, releasing heat into space. This cooling process has led to the moon undergoing contraction or shrinking in size over millions of years. An apt comparison is the deflation of a balloon when air is released from it. Although the reduction in size may seem modest, estimated to be around 500 feet over the past few hundred million years, it has notable implications for the lunar surface, resulting in observable changes. The second major factor influencing the moon's shrinkage is the tidal forces exerted by Earth. As the moon orbits our planet, the gravitational pull of Earth exerts varying forces on its near and far sides, creating a gravitational bulge on the moon's surface. This bulge undergoes dynamic changes as the moon rotates within its orbit. However, due to the lack of perfect synchronization between the rotations and orbits of the moon and Earth, the lunar bulge experiences continuous shifting and adjustment in response to Earth's gravitational pull. This continuous process of shifting and adjusting induces stress and strain on the lunar crust, further contributing to the moon's contraction. The combination of the moon's interior cooling and the tidal forces exerted by the Earth collectively results in a global contraction of the moon, accompanied by the formation of faults. In this context, a fault refers to a fracture or crack in the lunar rock where movement occurs. These faults predominantly take the form of thrust faults, characterized by one block of rock being pushed up and over another. On the lunar surface, these faults manifest as scarps or cliffs, some stretching tens of miles in length and rising hundreds of feet high. These geological features serve as tangible evidence of the moon's ongoing process of shrinkage and the deformation of its crust. The consequences of the moon shrinking become apparent through phenomena such as moonquakes and landslides. Moonquakes are seismic events akin to earthquakes experienced on Earth, resulting from the movement of faults on the lunar surface and the tidal forces exerted by Earth. Seismometers, instruments designed to measure ground vibrations, are employed to detect these moonquakes. The initial deployment of seismometers on the moon was undertaken by Apollo astronauts between 1969 and 1972. During this period, these instruments recorded over 28,000 moonquakes until 1977, when they ceased functioning. Some of the moonquakes recorded had magnitudes as high as 5.5 on the Richter scale, comparable to certain earthquakes observed on Earth. Landslides on the moon, induced by its shrinking, entail the movement of rock and soil down slopes, driven by gravity and the instability of lunar terrain. Factors such as moonquakes and faults significantly contribute to these events. Through observations made via cameras and satellites, scientists can capture changes in lunar terrain, revealing large landslides covering areas of several square miles and leaving behind trails of debris and dust. Both moonquakes and landslides, resulting from the moon's contraction, are subjects of immense scientific interest. They offer valuable insights into the dynamics of the lunar surface and provide clues about the moon's interior structure, composition, and thermal evolution. Studying these phenomena enables scientists to deepen their understanding of the moon's past and present, elucidating its unique characteristics in comparison to Earth and other celestial bodies. The implications of the moon's shrinking for future human missions encompass both challenges and opportunities. One significant challenge arises from the potential danger posed to human landing sites and habitats. Some faults on the moon are located near or within areas designated for NASA's proposed crewed Artemis missions, anticipated to occur in the 2020s. These faults could present risks such as moonquakes, landslides, and rockfalls, potentially causing damage to spacecraft, equipment, and astronauts. To mitigate these risks, it is crucial to map and monitor the faults and seismic activity on the moon. Additionally, careful consideration and selection of landing sites and habitats must be undertaken, taking into account geological hazards and environmental conditions. Among the challenges posed by the moon's shrinking for human missions, there also exist opportunities that hold significant scientific promise. The shrinking of the moon provides a unique chance to study its history and evolution in depth. The faults and landslides exposed by this lunar process reveal a variety of fresh rocks and materials that can be sampled and analyzed by both human and robotic explorers. These samples carry the potential to offer crucial information about the moon's origin, formation, and differentiation. Additionally, they can provide insights into the complex interactions between the moon and celestial bodies like Earth and the Sun. By studying these materials, scientists can reconstruct the geological history of the moon, unraveling its past volcanic activity, impact events, and tectonic processes. This information can help refine models of lunar evolution and shed light on the broader processes that have shaped the moon and other rocky bodies in the solar system. Furthermore, the exposed geological features offer opportunities for comparative planetology, allowing scientists to draw parallels between the processes occurring on the moon and those on other planetary bodies, including Earth. By understanding how these processes operate in different environments, scientists can gain deeper insights into fundamental planetary processes and the conditions necessary for the emergence and sustainability of life. In conclusion, while the moon's shrinking poses challenges for human missions, it also presents valuable scientific opportunities for advancing our understanding of lunar geology, planetary evolution, and the broader dynamics of the solar system. By capitalizing on these opportunities, scientists can unlock new insights into the history and nature of our celestial neighbor and deepen our understanding of the universe as a whole. Thank you for tuning in to Planet. If you enjoyed this video, please remember to leave a like and subscribe for more content on the wonders of the universe.